In part 2 of this video, we're going to go through and we're going to try to learn how to calculate relative atomic masses and kind of introduce some other pretty important conversion factors that are going to be related to different atoms and the number of atoms in a mole, and introducing molar masses as well. So understand that the atomic mass unit is going to be the way that we describe the masses of things on the periodic table. In other words, how much a single atom weighs is arbitrarily going to be determined to have something to do with this idea of an atomic mass unit. Now, it's all related back to the carbon atom, which is known to weigh exactly 12.00 AMU. So any other atom on the periodic table is actually compared directly to the carbon atom, which is nice for a couple of reasons, but also kind of misleading sometimes. We have, of course, gone through and related it to how much things weigh on a balance or how much mass something has, but that is the universal way to understand how mass is going to be assigned to our atoms. The average atomic mass is going to be the weighted average of things. And we're going to talk about how to solve this ourselves using percentages, which are also referred to as relative abundances. So each different isotope of an element is present in our environment in a certain percentage, and we use those percentages and how much those things weigh to determine the total average atomic mass of an element. So this is what we call a weighted average. Of all isotopes. And we're going to see an example here in a second. The best way to learn how this works is to actually do some math with it and see what we're actually talking about. So in order to calculate it, we're going to take the different percentages that each individual isotope are present at, and we're going to multiply and add them together to get the total atomic mass. Okay, so for this first one, we know that 69.15% of copper atoms in the universe are present at a mass of 929.601 AMU. And then we know that 30.85% of the copper atoms in the universe are present at 64.927794 AMU. So in order to figure out what our total mass is going to be, what we're going to do is we're going to convert, step one, convert percentages to decimals. And in order to do that, we're going to divide them by 100. So we're going to take our 69.15%, divide by 100. We're going to get 0.6915. And then we're going to do the same thing for our 30.85%, divide that by 100, and we're going to get 0.3085. Okay, the second step is going to be, and we're going to do this on the next slide, to multiply each atomic mass by its percentage, then add them together. So step 3 is actually going to be to add it all together, but we're going to go ahead and move on to the next slide to do this. Ooh. All right, so we're going to take our 0.69, was that 69? 15 and 0.3085. So again, we're going to multiply these by their relative atomic masses. Just give me 1 second, I'm going to find that information. All right, so when I do this math, I'm going to get a couple of different numbers. My final step is going to be to add them together. So if you work faster than me, that's okay. But I'm doing this in my calculator while I'm recording, so be patient. So this number comes out to be 43.50198 909. I know I'm carrying a lot of decimals here. We'll talk about sig figs at the end. One thing to know about sig figs with our numbers that we're multiplying here, atomic masses do not participate in sig figs. They do not get a say in the final number of sig figs, if you will. So when you add these things together or when you're multiplying them, understand that the percentage you were given is the only thing that has sig figs. So this number, of course, had 4 sig figs. This number had 4 sig figs, and we multiply them. We should only keep 4 sig figs in our final numbers. So I'm going to round my numbers to 62.91 and I'm sorry, not 62.91, 43.50, and I'm going to round this number down here to 20.03. My final step in calculating the total average atomic mass, add all values together. Ooh. So we're going to get the 43.50. Here, you just want to be careful about your sig figs. Remember that the final answer has the least number of decimal places. They both have 2 decimals, so our final answer should have 2. When you add those 2 together, you should get 63.53 AMU. And if you look at a periodic table, this is the number that should be underneath the copper atom on the periodic table. This is the average atomic mass of all of the isotopes that exist, and will give you the answer to the average atomic mass of something on the periodic table. This is that process that we're learning. Okay. And moving on to the moles. So this is one you may or may not already know. It kind of depends on your experience with the periodic table and chemistry in general, but the mole is going to be the SI unit that represents an amount. Just like a dozen is something that a baker might use, the mole is something that a chemist uses to tell how many atoms there are in a specific mass of a sample. For us, that's really good because if we weigh something on a balance, we want to know how much that number on the balance really means in terms of atomic numbers, as far as how many atoms are there in, say, a 50-gram sample of copper. There's not just one copper atom in that 50-gram sample, there's a lot of them. And we can figure that number out by using the mole and the numbers in the periodic table. So for us, a mole is going to be the amount of a substance that contains as many particles as there are atoms in exactly 12 grams of carbon-12. So again, everything goes back to carbon. Everything is related back to the carbon atom. Why? Don't know. I couldn't really give you a good reason for this. Historically, I think carbon was probably one of the easiest substances to measure accurately. So it was just the first one that someone weighed and decided a few different things about. Avogadro's number then is the number of particles in 1 mole of a substance. So for instance, if we have, and I'm going to just write times 10 to the 23rd atoms equals 1 mole. Okay, so this is going to be our first conversion factor using atoms on the periodic table. We want to make sure we understand when we write this, remember that we can always write the 2 different fractions. So there, of course, going to be 2 that we can write. Remember, just like everything else, we can put the number of moles on the top. Or we can put the number of moles on top, and we can put the number of atoms on the bottom. Okay. Yes, we will be doing math with this. You have conversion factors, and something we can do is determine how many atoms there are in a single mole or in many moles, and we'll do some practice problems here in a second as well. The mass of 1 mole of a pure substance, however, is going to be the molar mass of a substance. So now we can take our idea of the mole, knowing that there are a certain number of atoms in a single mole. That's really useful, but we don't always want to report numbers in terms of atoms because we're not actually counting individual atoms. What we're actually using on a balance in a classroom or in a lab is going to be something that reports a number in grams. So it would be more useful if we could relate a number to grams. And could we directly calculate how many atoms there are in a specific amount of grams of a substance? Yes, we could, now that we know what the mole is. For the periodic table, though, the molar mass is going to be something that we get from the periodic table. So the mass is going to be on the periodic table. You're going to see that we can use two different units for the different numbers on the periodic table. So for instance, for the copper atom that we just calculated, we said that the overall mass was going to be 63.53 grams in 1 mole, or we could have reported it as 63.53 AMU, atomic mass units. So this is more what one atom weighs. And this is and this guy is more what 6.022 times 10 to the 23rd atoms weigh. Remember that 1 mole is this number of atoms, so when it comes down to it, we can simplify that number on the bottom on purpose. Okay. So just giving you an idea here, if we look at the mass of something in the periodic table, remember we're looking at that bottom number, what this is saying is that 1 mole of H atoms will equal 1.008 grams. We can also say that 1 H atom weighs 1.008 AMU. And that goes for any atom. We could talk about magnesium and how it weighs 24.305 grams per mole, or we could talk about how 1 atom of magnesium weighs 24.305 AMU. It's so convenient that AMU and moles line up, I know. Let's not ask too many questions about that. All right, so in class tomorrow, because I will be back in class tomorrow, we're going to talk about how to do gram to mole conversions. We're going to spend some time doing these in class, of course. We're going to use molar masses as our conversion factor. We're going to go through a few different problems. For now, I just want you to kind of understand how to read the periodic table and how to interpret the numbers that are on the periodic table in multiple ways. Remember, we can talk about the atom weighing a single amount in AMU, and we can talk about a mole of atoms weighing a single amount in grams. All right, that is all for today. Make sure that you have notes ready because we will take a brief lecture quiz in class tomorrow at the beginning, while we also handle some other business like turning in some stuff from the week. Have a great day.